We move on to the final talk in this session. It's by Jason Corliss, the Spatial Heterodyne Interferometric Molecular Cloud Observer, a suborbital mission scheduled for launch in 2027.
Okay, fair question.
Oh, wow.
I didn't feel bad.
You did. Wow. Wow. All right. It's a whole other talk. Yeah, we can use that or you can use the right arrow. This is
Okay, thank you. Hi, my name is Jason Corliss at the Lunar and Planetary Lab, here to talk about SHIMCO, suborbital sounding rocket flight scheduled for launch in June 2027. Here's the excellent team that we have. I'm PI of COI, Walt Harris, Erica Hamden, Han Chung, and then we have a great group of graduate students and undergrads and engineers, as well as our space grant awardees for the NASA Arizona Space Grant program. So I'm just going to give a brief overview of the mission with the technology that we're trying to advance and the science that we're trying to attain, and also some of the ConOps that we've been considering and the target list that we're narrowing down as we go. So SHIMCO stands for Spatial Heterodyne Interferometric Molecular Cloud Observer. We're going to be looking at star forming regions and nearby molecular clouds at very high spectral resolution using a spatial heterodyne interferometer. So there's actually three key technologies. There's a new one that we're going to introduce in this mission, which is AI target discrimination, which Joanna is going to lead on along with Jehan, as well as JPL's fabricating an EMCCD that we're a photon counting EMCCD that we're going to integrate into the payload. So we're building the housing and cooling requirements for that. And that's going to be delivered. So I should say that this mission kicked off about 1 year ago. It's a 4-year program. And so we still got about three years. We're going to wrap up again, the launch in June 2027, and then do the data analysis at the beginning of 2028. So sounding rockets. So I'm just going to go over sounding rockets really quick and what rocket we are flying. So you can kind of see back there, but we have they're sort of named by the motor stack that they have. So we're going with a 2-stage, which is the Black Brant 9. So it's got a Black Brant for the main motor. The initial phase is a Mark 70 Terrier Malamute, which will be our sort of kickoff booster. We reach a apogee of about 370 kilometers. Our key sort of discrimination for our science acquisition is about 100. We got to be above 100 kilometers. So we only get about 7 minutes of actual data collection, science data collection. So the whole flight is 15 minutes from launch to impact. So it's a very busy 15 minutes, I should say. So you're getting data real time, and it's just a very hectic, but very fun. And so these programs are great for students, for graduate students to learn. It's a very hands-on program. There's not as much red tape as small sats and all that sort of thing. Also, upcoming PIs, because it's a full mission life cycle from beginning to end. And that's with, so this is with the NASA Sounding Rockets Program Office, which is in Wallops, Virginia. This is where we take our payload and integrate, do our vibe testing and make sure that we're ready for launch. And then we're going to be launching out of White Sands, New Mexico. Let's see, I think this flight will get about 90 kilometers for the distance in White Sands. So it's actually a relatively high and long range flight from the White Sands facility. So this is This is actually, we've changed our payload. I should say that. We started out, we were going to refly one of Walt's previous payloads, which had a 22-inch skin. I don't know if I can point with this, but you can see it's a 17-inch rocket skin is the front section. And we learned that we can get about an extra 50 seconds of flight time, which is significant since we only have 7 minutes, or we have whatever, 6 minutes and 10 seconds before that. So we could reduce the drag and reduce the weight by dropping that larger skin with the telescope section structure, because that initial or the last launch was to study, initially to study Jupiter's aurora. We were going to image the aurora. So we had a large telescope in there, which we don't need for this one. So we're actually building a whole new payload for this flight. So we're still in some of the initial phases. We have time, but we got to start really getting things going. The main technology that we're advancing in space qualifying is what Walt and I have been working on for a number of years together, which is spatial heterodyne interferometry, which is a compact, high ATON instrument that achieves extremely high resolving power in a very small format for spaceflight. So that's one of our main. This grading is from another program that we have over in the lab, which uses this is the first of its kind, dual ruled symmetric facet grading. But essentially, you have the bare bones of it is a roof mirror and a flat mirror, symmetric groove grading, and the beam. And I have another. If I can get this video to work, I'll show you how it works. Let's see. Last time I couldn't get this video to work, but let's see if I can do that. There you go. No, I got to stop it. So this is actually a prototype that I built and took up to Kitt Peak many moons ago to look at comets in the Jovian system. So this is a to scale model where I overlaid a Zemax model and a CAD model of that layout. Oh, it stopped already.
Pressing it again.
Did it work when I did this?
There it goes.
So the beam's coming down from the telescope to the grating where it beam splits, and then it counter circulates, the roof mirror folds the beam down, reduced on the lower half of the grating, and then it recombines and exits out, and the interference happens enough to the detector. The interference happens roughly halfway in between, so you're interfering two coherent plane waves. The incoming light is collimated, and we get that. Let me go back to that. So you get an interferogram like this, and the roof mirror does two things. It breaks the symmetry, so you can get a tilt of the fringes that on one side of the heterodyne is in that direction. On the other side, I should have had a slide of the power spectrum, but essentially it doubles your effective bandpass that you can resolve while maintaining on axis where you get the highest fringe contrast. So I'm not going to go over the JPL, the MCCD fabrication. I'll just get into the science a little bit. So we're going to be looking at molecular hydrogen emissions and FUV. We are going to target around 160 nanometers. The Werner band is very broad. It goes from 140 roughly nanometers all the way to 162 nanometers. But the coatings that are available right now, you can get nearly 100%. It's like 98% Goddard is achieving at 160 nanometers. And so we have so many reflections, and we're going to be really starving for photons in our brief 7 minutes of data acquisition. So we've decided to just target on that range. They're also the brightest lines in the spectrum are right around 160. So we are going to do a narrow, very high resolution bandpass. I should mention that Erica Hamden's, this is her real area of expertise and science interest in these star forming regions. And Hyperion, which is another small sat that she has proposed and is proposing another longer term mission to study these star forming regions in a broader look across the galaxy or the universe. And that will do a diagnostic to get the temperature, which is the relative line strength. If I can go to the next slide. So there's two ways to do it. You can either look at the relative line strengths of multiple lines in your bandpass, and Here we just look at the bottom one where we're targeting in. This is around 160 nanometers. And this is a temperature jump as you go from 100K to 3000K to look at the physical conditions of the star formation regions. Temperature is a key diagnostic. So there's two ways to do it. We can look at, like Hyperion was doing, which is look at the relative line strength of these lines as a function of temperature. But with SHS, we can actually, we're such high spectral resolution, we're going to be able to measure directly the thermal width of an individual line. So you get the full width at maximum. It's expected it'll be thermally dominated, the line width. So we'll have two ways to measure that. Should increase our confidence in that measurement by having both diagnostics within the bandpass. And so this is some great work that some of Cole and some of our new space grant students have done in target selection, because there's many OB star and molecular cloud regions to look at. Again, we have a very short window to acquire our data, so we got to pick our brightest, best target, and that it would be one with the lowest background, because as we're in an interferometer, we're also susceptible to what's called multiplex noise. So we want low scattered light, low background, but high signal from our target emission lines. So we're looking at a number of different molecular cloud regions, and they did it using the FIMS and MIPS data, did a survey, and honed in on essentially the Rho Ophiuchi. Originally, we were going to look at the Orion Nebula. Now we're going to look at Rho Ophiuchi. It looks like it's going to be quite a bit brighter with less background. Don't want to run over and keep people too late, but here's a zoomed in. So this shows the EV minus B minus V map, which is a reddening map, which is a measure of sort of the background continuum that we might worry about, and then the H2 anticipated intensity. Of course, this is the FIMS data is very shoddy, and plus it's a much larger spatial pixel. So we're going to be honing in around one of these OB stars for our target. And so we're going to have roughly three targets in our quiver. Potential targets, since we're going to make real-time ConOps decisions, we're going to look at our first one, depending on our signal rate, how many photons per second we're going to get, anticipate some sort of signal noise level with that target to tell us whether we can transition to target number 2, target number 3, or have to remain on target number 1 the whole 7 minutes to acquire some significant data. So I think that's about it. I'll wrap it up.
Okay. So how much time you have? 7 minutes on that?
Yeah, 7 minutes above 100 kilometers. So yeah, up to 7 minutes per object.
And how do you actually stabilize your observation?
Well, NASA does that. So we tell them what our requirements are for jitter and for pointing. And so we've already gotten through the definitions package. I think our jitter is an arc second or 2. Our field of view is around, I should have said that, is about 0.3 degrees by 0.3 degrees. So we want to stay off the O star, so it's not in our field of view. So we're looking right off the limb of the star, try to get some of the most active and brightest emission. But yeah, NASA takes care of all of that. We have to tell them how many objects we have, so they have enough gas tanks to be able to point the rocket once we're in space, and what sort of stability we need.
Looking at the side.
No, I should go back to that. We're looking out the butt of the rocket.
So the telescope is actually defines the diameter of the rocket, or more or less.
Well, not necessarily. So our telescope's only, in this case, is only going to be about 3 inches, and the rocket payload is 17. What the rest of you can go the Brandt variants that I was showing you, that they're all 17 as a base, but you can go up to 22 for a transition if you need more space for your payload package. Some of those other rockets are, I think, 15 inches or less, but we'll populate the deck. So you have the Star Tracker 5000 in there, which needs some space, to be able to show where you're pointing and things like that. So besides our telescope, you have other equipment.
More questions? Yes.
If you select a wavelength, what is the spectral range that we can operate in?
If you expect to,
Yeah, if you are a central wavelength, for instance, what is the spectral range within which you can operate in?
well,
If you have to do a tune like spectral scan, is it possible with such systems?
in this system, no, the one that we're flying, it's not a scanning, so it's a static system. It's set. So your band pass is defined by how many pixels you have on the detector and your resolving power. So you have such whatever dispersion it is. So if you have
But
a-
in a scanning system, what have you demonstrated? Band pass, spectral band pass.
well, yeah, we have some different types of scanning systems. One is a scanning system that we're working on right now in the lab, which is actually has on motors and scans the mirrors where you can do a factor of 4 in wavelength. I think we've done already from 300 nanometers to 700. So there's other technologies we're working on, which is multi-order. So you're actually diffracting multi-orders at the same diffraction angle, different order wavelength pair has the same angle. And so you look at discrete band passes across the wide range. There's different ways you can do it. In this case, there's also different problems with that. So you'll introduce multiplex noise and different noise when you're putting it all on the same detector. So for this mission, we just want the cleanest, brightest part of the spectrum. And that's without any more, added noise. So we don't know exactly how bright it's going to be is the issue. So.
Any more questions? All right, thanks, Jason.
You bet.